So today we will be learning about maximum power transfer theorem. Okay, so we will be learning about maximum power transfer theorem. We have already completed our Thevenin's theorem and Norton's theorem. So it is also known as in short form MPTT theorem. So suppose we have a Thevenin's equivalent circuit of any circuit. We have, let's first look at the proof and which is a condition and how to know which resistance we will get the maximum power. So suppose this is our load RL, this is our RTH, this is our voltage Thevenin voltage, and this is the Thevenin's equivalent circuit. So first of all, we know that current is flowing I. So first of all, the load resistance must be not fixed and it should be variable. So we want to know through this theorem is when, for which value of RL maximum power will be delivered to the load. Okay, so we want to know for which value, since it's a variable resistance, for which value of RL it should be equal to, so it should get the maximum power out there. Okay, so we all know that I in this circuit will be equal to VTH upon RTH plus RL, correct? Total resistance upon the total voltage upon total resistance. Okay, series, both are in series. So now what is power? Power is nothing but power at RL, power dissipated or delivered to RL, not dissipated, power delivered to RL by a load is equal to I square RL. So this is variable. We want to find the value for which the power is maximum. So this is something what I square means. This is the value of I. So it is VTH square upon RTH plus RL whole square into RL. So this is power. So we know that to maximize this equation, what we have to do is dPRL upon DRL, because this is the variable unit, must be equal to 0. So d by, it implies that d by, so this is the power equation. Okay, d by DRL of VTH square RL upon RTH plus RL square must be equal to 0. So this is, since we have function in both numerator and denominator, so what we will use is u by v, differentiation of u by v. Okay, let me write a formula for you. Okay, so the differentiation of, it will be differentiation of u of x upon differentiation of f of x is nothing but, first what you have to do is that, first you have to do differentiation of ux. Okay, u dash of x into fx, okay, minus f dash of x into ux, okay, upon fx of whole square. So this is how you solve differentiation of these two. So what we will do is that differentiation of this unit into this first term, so it will be nothing but VTH square into RTH plus RL whole square minus, now differentiation of this will be 0, this is independent of RL, and this will be 2RL. Okay, so it will be nothing but 2RL. Now this equation will be as it is. Okay, so 2RL we have put already, and this equation will be as it is. Okay, or what you can do is that since this equation will be as it is, you can just make a whole multiplied by and put RTH plus RL whole square, okay, upon RTH plus RL whole square. Done. So I want this equation to be equal to 0. So if you look closely, from this equation we have arrived to the point that RTH plus RL whole square minus 2RL RTH plus RL whole square is equal to 0. So what you can do again is, so this is nothing but, since you have arrived to this point, you can write this as, you can open this whole equation, RTH whole square plus 2RTH, okay, 2RTH 2AB RL plus RL square minus, you can again multiply this thing, okay, 2RL into same thing, okay, RTH whole square plus 2RTH RL plus RL whole square is equal to 0. So we have already done this thing. So it will be nothing but, you can solve this equation. It will be RTH whole square plus RL whole square plus 2RTH RL, 2RTH RL minus 2RTH RL minus 2RL square equal to 0. So what you will finally get is that, so you can just simplify these things. It will be RTH whole square, these terms will be cancelling out, okay, and minus of RL, this is 1 and this is minus 2, RL whole square will be equal to 0. Implies that you got a condition for which the power will be maximum. The condition is nothing but RL, since it will go that side, RL equal to RTH. So whenever the value of the load, will be equal to RTH, that's the condition for maximum power transfer. Okay, so graph is like this, okay, you get a maximum power, for RL value equal to RTH. This is the maximum power, this is the power graph, okay. But always remember, the efficiency at maximum power is only 50%, okay. So the efficiency is not that much at maximum power, and hence we always not deliver the maximum power to a load. So if we now look at, the steps to solve maximum power transfer theorem is: 1, calculate VTH, calculate RTH, put the variable load equal to RTH, calculate current in the Thevenin's equivalent circuit, I at the Thevenin equivalent circuit, and maximum power will be equal to, I load square RTH, that is equal to I square R, which will be equal to this I square multiplied by this RL, which will be equal to RTH. This is all about maximum power transfer theorem. We have already know how to calculate VTH, RTH. If you haven't checked those videos, you can go to my playlist and watch that. And moreover, we also have seen some cases of dependent sources. Also, we can get sometimes, suppose, okay, after the problem we will see that special case, okay. So now look at a problem, okay. Just question: find value of RL for maximum power transfer, power transfer, power transfer, and also P max. So the circuit is given. So this is the circuit given. This is the RL. This is 10 volts. This is 2 ohm resistance. This is 2 ohm resistance. This is given as 10 volts. Okay. So this is 2 ohm. This is 6 volts. This is 2 ohms. And this is 3 volts altogether. So this is the circuit. एक to आस्ते tip. So this is the circuit. So first step is to calculate VTH. For VTH we have to remove the loads from A to B. Okay, so the new circuit will look like. This is how the new circuit will look like. Okay, so I equal to will be 0 in there, and here I will be flowing in this direction. We have already the equation. So now only the current will be flowing in this loop, since it's an open circuit. For finding VTH is nothing but VA minus VB. Okay, this is A, this is V. So we will start from here and again come back to here. So we will write all the potential drops over here. Okay, so first calculate the current. So this is the first step. So KVL at loop 1, it will be equal to 4I plus 6 minus of 3 equal to 0. We start from this point and completed the loop. So M plus the 4I is nothing but minus of 3 amperes, and I is equal to nothing but minus of 3 by 4 amps. So now VTH will be equal to, let's start from here, I 2I plus 6 minus 10. So what is 2I? So 2I is nothing but is equal to 2 into minus 3 by 4 plus 6 minus 10 is equal to nothing but minus of 6 by 4 minus of 4. So VTH is nothing but it will be equal to, so minus of 4 into 4 16, and this is minus 22 by 4. If we divide by 2, it will be nothing but minus of 11 by 2 equal to minus of 11 by 2, which will be equal to minus of 5.5 volts. Since VTH is equal to negative, that means VA minus VB is equal to negative. Hence VB is at higher potential. Okay, VB is at higher potential, so the negative terminal will be connected to the A side. Okay, so we got this up to, we got this circuit. Okay, this is 5.5 volts, so negative terminal is connected to the A side. Okay, that's it. So now we have to find the value of RTH, and that will be itself our load. Our load will be also equal to RTH only for maximum power, correct? Power. So now to calculate the RTH, what we have to do, we have to short circuit this. Okay, we have to short circuit the voltage sources and open circuit the current sources. We have already discussed. Okay, so we have to short circuit this also, this and this. So now total RTH, to calculate total RTH, we can see that these two are in parallel, and the net will be, after solving this, it will be in series with this 2 ohm resistance. Okay, so the parallel of 2 and 2 is nothing but, so 2 parallel to 2, RTH calculation will be equal to 2 parallel to 2 plus 2 ohm. Okay, so 2 parallel to 2 is nothing but 2 into 2 upon 4 plus 2, so it will be 3 ohms. Okay, so 3 ohms is our RTH. Okay, so what we have done is that we have short circuited with this short circuited all the potential sources and calculated the RTH. So since these two was in parallel, same voltage across two terminals, I have replaced this part with just a single resistance of 1 ohm, and which will be coming in series with this resistance. So RTH will be equal to 3 ohm. So this is the equivalent circuit, and now I equal to 5.5 upon total resistance 6. This is I square into resistance is 3 ohm. This will be the P max. So I hope you understand how to solve maximum power transfer theorem. And now one special case I will tell you. If suppose only dependent sources are there, we have already shown that the RTH value sometimes have came negative value of RTH also came. In that case, the I will be equal to VTH upon RTH plus RL. So the RL value for the maximum transfer will be the mod of, suppose it's minus 5 ohms. Okay, so it will be just plus 5 ohms. If the resistance RTH is coming negative, so the for maximum power RTH will be just mod of the so R load will be mod of RTH. Just take a mod of RTH, so it will become infinite. It will become 0. So the equation of current and the max P max will tends to infinity. Only in case of negative Thevenin resistance, in some cases of dependent sources only. Okay, otherwise this is the method how we solve the problem. Thanks for watching.